Hello everyone. In our last lecture, we talked about continuity of a function at a point on an open interval and continuity everywhere. And we also talked about discontinuous functions and two types of discontinuity, the removable and the non-removable. In this session, we are going to be looking at continuity on a closed interval, and we will do some examples of special cases of continuous functions. So let's start with the continuity on a closed interval. A function f is said to be continuous on the closed interval a to b when the function first is continuous on the open interval a to b, and the limit of the function fx when it approaches from the right hand side is equal to the function of a, and the limit of the function as x approaches from the left hand side, b minus of the function fx is f of b. So let's look at from the graphical point. So here is our closed interval a to b. Remember, we represent a closed interval by the square brackets. Now, clearly, according to this function to be continuous, it has to be, first of all, continuous in the open interval a to b, and at the end points, it has to be right continuous, that means coming from the right-hand side, and it has to be left continuous when you're coming from the left-hand side at b. Okay, so at this point, it is the limit as x approaches b minus of this function fx equals f of b. Remember, the function is only defined from a to b. There's nothing outside b. So the limit of this function fx is x approaches from the left-hand side, that's a red pointer here, equals the value of the function at b. Now, for the right-hand limit, it's coming from the right-hand side, approaching a from the right-hand side. So this means that is the limit of the function fx as x approaches from the right-hand side, which is denoted by a plus, equals the value of the function at that point, which is f of a. Remember, guys, this point is f of a. And so that's what the limits are. Now, let's look at the examples over here. This is an example which we have seen earlier. This is a function which is of a semicircle, and it's given by fx equals square root of 1 minus x squared. Now, the first thing is, before we do the limits, let's talk about the domain. Now, clearly, this is a square root function, so it can only take values where the inside part of the square root is positive, which we can easily figure out by, that means 1 minus x squared is greater than or equal to 0, or minus x squared is greater than or equal to minus 1, or multiplying by minus 1, we get x squared is less than or equal to positive 1, or x is less than or equal to plus minus 1. We're basically between minus 1 less than or equal to x less than or equal to 1. Okay. So that means this is the domain of the function. You cannot have values beyond minus 1 or have values which are on the right-hand side of 1. So the domain of the function is minus 1 to 1. Now, clearly, by looking at the graph, this function is continuous, definitely, in the open interval minus 1 to 1. So let's look at what happens at the endpoints, minus 1 and 1. Now, at minus 1, which we just have learned from our previous slide, the definition, that at minus 1, which is our a, the function is going to be right continuous, and from the on 1, which is our b, it's going to be left continuous. Okay, so which is interpreted as -1, remember, is our a here. So remember, it's -1, it is a to b, so this is our a, this is our b. Keeping in sync with the previous slide. So let's talk about -1. So the limit as x approaches -1 positive of square root of 1 minus x squared, what's happening? As we are coming closer to -1 from the right hand side, that's what we're looking at, the value of the function is approaching 0. The answer is 0. When we are coming from the left hand side at 1, that's our b, the value of the function again approaches 0. Okay, remember, b is our 1 and a is our -1. So this is an example for continuity on the closed interval. Let's look at special cases of continuous functions and how do we do the math. Now, find x values where the function is discontinuous and tell which of them are removable. So here is a piecewise function, and notice when we initially look at the function, when x is strictly greater than 3, the function is 3x plus 1, which is a straight line, and we know this is a polynomial, so this polynomial function on its own is totally continuous. But when it is put in connection with another function which is inside the piecewise function, that means it is x squared plus 4. And that's where the change happens. Remember, the piecewise function, the change is happening at 3. So from 3 on the left hand side, that is x is less than equal to 3, it's a squaring function. And when x values are strictly greater than 3, it becomes a straight line, which is given by 3x plus 1. So we would like to know whether the function is discontinuous and if it has discontinuity, and what are the values where it has discontinuity, and if it is removable. So these are the two questions. Okay, first we're going to do it by the analytical approach. Then I can also show you with the help of a graph. So let's start with here. I think I'm going to start with the graph, which will make much more clearer, and then we go the analytical approach. Yeah, that's much more better. Okay, so let's draw the graph, guys. Okay, so in this one, 3 is the point where there is a change. When it is greater than 3, that means my values are on the right hand side of 3. This is a straight line, 3x plus 1. Okay, so let me just draw a straight line going like this. It's a straight line with a positive slope, so I just make a, I just going to eyeball and just make a straight line. Okay. Now, at 3, we do not know what it is, but we definitely know it is not including. It's a strictly greater than sample, so that means there's going to be an open circle. Just remember that. Okay. When x is less than equal to 3, so I'm going to use a blue pen here. That means the values are on the left-hand side of 3. The function is a squaring function, x squared plus 4. Now, if you remember, that means you will have a parabola and it is going to be opening upwards. So it's something like this. It's going to be in a parabola and opening upwards. The only thing is that's where the value is having an equal to symbol. That means that's going to be a closed dot at the value at 3. Okay, so let's start with that. What would be that value? We have to also look at that. So it's x squared plus 4. So when I plug in 3 here, so f of 3 means what? That's the function we have to go. It's 3 squared plus 4. What is that? It's 9 plus 4, 13. Okay, so I am going to draw a 13 here so that I don't mess it up. I might have to redo it again. Okay, let me just draw that. So it's going to be at 3, suppose this is 13. I'm going to eyeball the number. Now this is going to be a closed dot. Okay, we still have to draw the line 3 plus 3, but I need to know what the value is. Okay, so let's look at this one. At 3, we know when it is greater than 3, it's a straight line. But I need to know if that value, what is the value at 3? And that is going to be a point with an open circle. So when I plug in 3 in this first equation, 3x plus 1, what do I get? So 3 times 3 plus 1, that's a 10. So that means, and I'm going to use green, and let me use all green to make sure that what values I'm looking at. Now to find the value of the function at 3x plus 1 when x is strictly greater than 3 or 3. So we are going to put, so f of 3 here. So this will be giving me 3 plus 3 plus 1. Do you see that here? So let me not put f of, okay, so f of 3 when x is strictly greater than 3. Okay, so let's just write 3 times 3 plus 1, which is going to give us a 10. Now remember, this is f of 3 for this scenario. Okay? Okay, I don't want the value. Yeah. So this is f of 3 for this case. Now here, because it's a stricter symbol, that means that is going to be represented in a graphical scenario by an open circle. And 10 is the value of the function. So we will have an open circle right here. And then after that, the value is going to be represented by a straight line, like this. Now, notice when you are looking at this graph, clearly at 3, there's a discontinuity. And that discontinuity is represented by a jump. Notice the left-hand limit is different and the right-hand limit is different. So clearly, this is a point, this function is going to give us a non-removable discontinuity. Okay? Okay, so let's look at this one. So, here, just looking at the graph, we know that in this function, x equal to 3 has a discontinuity and it is a non-removable discontinuity, just by what we have learned in the previous session about non-removable and removable discontinuities. So this is for this, guys. Now let's look at from the angle of analytical approach. So I would like to know, what is the limit of this function x approaches 3 minus, and I forgot to write, guys, it should have an fx here. Okay, yeah, it should have an fx. It's a typo, guys. So this is fx equal to, this is fx equal to, okay, fx equal to. Okay. Now to find this limit as x approaches 3 minus of the function fx. Now 3 minus means all the values which are less than 3. So what I'm going to do is, guys, I'm going to open so I'm going to remove this, and then I am going to show you using this whole. Okay. Now let's look at this function which is given again. So when it says x approaches 3 minus, and you're for the limit, that means that to look at all the values of the function which are x is less than 3. So that means you're going here. Okay, so that's where we are going. So that means this is going to be the limit x approaches 3 minus, my function is going to be x squared plus 4. So let me be consistent with my the pen. So this is going to be fx. I forgot, as I said. The left hand is being represented by the blue pen, guys. So it's limit x approaches 3 minus. Now this function would be now x squared plus 4, which is equal to, you substitute the 3 here because it's a nice little polynomial. So just do the direct substitution. You get 13. Okay, now let's look at coming for the right-hand limit, that is limit as x approaches 3 positive of the function fx. Now that means we're going to look at the top function value we're going to look at this. So this is the limit of the function is going to be now 3x plus 1. X approaches 3 positive, which we already know the value is 10. So clearly, the left-hand limit is not the same as the right-hand limit. So this is a scenario where the left-hand limit is not equal to the right-hand limit. Now, if you remember, I've talked about when a left-hand limit is not equal to a right-hand limit, that means we are going to have a non-removable discontinuities. You can see it from here. Remember, this 3 minus means I'm having a left-hand limit. And 3 positive means we are having a right-hand limit. Okay, now let's look at the next case. We are again given a piecewise function where the function fx is 3x plus 1 when x is strictly greater than 3 and x squared plus 1 when x is strictly less than 3. Okay, in this case, what is the value of the function at 3? When you look at this piecewise function, I do not see in the very last column an equal to sign. So that is an indication that f of 3 is undefined. That's the meaning of it, guys. Okay, again being consistent with our colors of minus in this. Okay, now, so first of all, the function 3 is undefined. That automatically tells us that this function is discontinuous at x equal to 3. Okay, so from this, just f of 3 being undefined gives us that the function fx, here this one, is discontinuous at x equals 3. Okay, now we'd like to know what kind of discontinuity is it? Is it removable or non-removable? Okay, now when I look at this one, so remember the removable discontinuity has a very simple thing that the limits have to exist. Remember the left-hand limit is the same as the right-hand limit? That was the way we learned about, the simplest way of looking at it. Okay, so let's look at the left-hand limit and the right-hand limit. Now, first of all, in this one, this time I'm going to start with the analytical approach and then show you the graphical approach. So here it is, limit as x approaches 3 minus of f of x equal to. Now 3 minus, guys, remember, means the left-hand limit. 3 minus means you're looking at all the values of x which are less than 3. That means you're looking at the second row of this piecewise function given by x squared plus 1. So this is limit x approaches 3 minus f of x is x squared plus 1. Clearly, this is a nice little polynomial, and just apply the normal limits, substitute. You get 3 squared plus 1, you get a 10. Okay, now let's look at the right-hand limit. So limit as x approaches 3 positive of the function fx. X approaches 3 positive means you're looking at all the values of the function x which are greater than 3. So we are looking at the top row of this piecewise function. So that means this will be limit x approaches 3 positive of the function given by 3x plus 1, which will be limit x approaches 3 positive 3 times, again it's a nice little equation, 3 plus 1, which will give me 10. So clearly the left-hand limit is the same as the right-hand limit. Okay, so here the left-hand limit is the same as the right-hand limit. So that means we are having a removable discontinuity just from doing analytical approach, okay? So we have a removable discontinuity. Now that's all done analytical. Now I'm going to show you the graphical approach. Okay, let's draw a graph here for this function. Notice individually on this piecewise function, these two functions on its own in this piecewise, are basically are polynomials, and polynomials we know continuous everywhere. It's only the point 3 in this piecewise function which makes the decision whether it's going to be continuous everywhere or not. Now the first thing is, because it does not have that equal to sign, that tells us that we are going to have a hole over there. That is the key point. Remember, key point is there's nothing happening. There's a no equal to sign in the last column of this piecewise function. So that means the function at 3 is undefined and we're going to have a hole. That's it. Just make a little hole. I do not know what that value is. It will depend upon the left hand and right hand limits, guys. Okay, we know there's a hole. And also, what we know from the left and the right hand limit, these limits are approaching 10. So basically, it gives me an insight, hey, that value where the hole is going to be a 10. Just from my simple knowledge of how to draw a graph of a piecewise function. There's no calculus involved, guys, at this point. Just from my simple knowledge, if the limits are approaching 10, that means that is my 10 here. Okay, now let's look at the function fx here. So this fx, as x approaches 3, is 3x plus 1. At 3, when you substitute, it gives me 3 times 3 plus 1 gives me a 10. And x greater than 3, it's a straight line. Okay, so just be consistent with my colors. And we'll just simply eyeball it, make a straight line. Okay, now let's look at the function when x is strictly less than 3. That means all the values which are on the left-hand side of 3. That's x less than 3. Now that function is given by a squaring function, which is given by x squared plus 1. X squared plus 1, if you remember from your algebra pre-calculus days, it's a parabola which is opening upwards and crosses the y-axis at 1. And that's how the graph looks like. So clearly the limit exists, but because there is no equal to sign in the piecewise function, that means the function at 3 is undefined. And the left-hand limit is the same as the right-hand limit. That means it's a removable discontinuity. So I have given you various ways of looking at the problem, graphical or analytical, and things which you have learned earlier in your algebra or pre-calculus classes, that you can easily do the work and get the answers for discontinuity and what kind of discontinuities it is. So when you apply the limits, that means you're coming from the calculus, and if you don't use any calculus, you just draw the graph and you will still get the answers. Okay, now let's go to another special case of a function. We have seen this function before, and I just showed you the graphical way of looking at the problems and making your analysis. Now here we will actually do the analytical approach. And I said earlier that when we're going to do the analytical approach, I will actually do what is the greatest integer function, explain things to you, and then we will do the limit approach here. So let me start with the limit of this function, which is of absolute value, the greatest integer of x minus x. So before I do all this function values, I am actually going to do the math here for a greatest integer function. Okay, let's look at this one. Greatest integer function. Now remember, you do not have a graph for you. So you are going to totally depend upon the definitions and the analytical approaches to find the limit values. So before we go, as I said, let's talk about what's the greatest integer function. First of all, the notation is given like this. The greatest integer function means it is the integer, the greatest integer. It is of all the integers, that is the greatest integer less than or equal to x. Okay. Less than or equal to x. So let's do some math here with examples. So if you have a function, so if my x is, say, 1.5. So in other words, let's draw the number line. That's the best way to do these problems. Okay, let's draw a number line. 1.5 lies between 1 and 2. So that's my 1.5. Okay. Now, according to the definition of greatest integer, it means what are the value, all the integers which are less than 1.5. So you have integers, what is it? You have 0, 1, 2, minus 1. So out of all the integers, which is the greatest is 1. And that's the answer to this question. Okay, let's take another example. Say 3. Now, if you get over here, this is my 3. So look at all the integers which are less than or equal to 3. The number is 3. Okay, let's talk about 5. So that means you have 4, you have 5. So greatest integer less than or equal to 5 is 5. Let's look at, say, 5.5. That means it's a number lying between 5 and 6. So what is the greatest integer less than or equal to 5.5? 5. Let's look at a value which is 4.5. Now that's a value which lies between 4 and 5. So what is the greatest integer less than or equal to 4.5? It's a 4. Now these were all positive numbers, so let's look at some negative numbers. The greatest integer, say, okay, let's start with negative 0.9. So that's a number very close over here between minus 1 and 0. So this one, all the integers which are less than, this is minus 0.9, you will have what? You will have minus 1, minus 2, but the greatest integer is minus 1. What about minus 2.3? Okay, that means it lies between minus 3 and minus 2. So this is minus 2.3. So the greatest integer is minus 3. So that's how we get our greatest integer function. Okay. Now, if we draw the graph, so let's look at the graph here, guys. Let's pick one number also here. So 0.3. What about this one, guys? It's here. So the greatest integer is 0. So if I draw the graph of a greatest integer function, how will it look like? Say 0, 1, 2, minus 1, minus 2. Now, if I have any value, so if the greatest integer is 0, so what is that greatest integer? 0 is 0. But the moment we have any value greater than 0 point, and so let me use a marker here. So any value which lies between 0 and 1, the greatest integer is going to be a 0. But the moment it hits a 1, what is going to happen? There's going to be an open circle, and at 1, the value becomes 1. And any value between 1 and 2, any value we take, say 1.5, between 1 and 2, it's the greatest integer is a 1. So we continue to draw a horizontal line till we reach 2. What is going to happen? There is going to be a jump because the greatest integer for 2 is a 2. And that's how we will see graphs going. Similarly, let's look at this. Any value between, say, negative 0.9, between minus 1 and 0. At 0, it is 0, but between minus 1 and 0, the value is minus 1. The moment it hits 0, it becomes 0. Similarly, any value between minus 2 and minus 1 will have the greatest integer to be minus 2. with a filled circle at -2, but the moment it hits -1, it jumps and there is an open circle. So that's how this is a staircase thing we see for the graph of the greatest integer function, fx equals this, the greatest integer function. Okay, now let's come back over here and look at the problem. Now, for this graph, let me draw the graph here once again so it will make it easy for you guys. So we have 0 to 1. You see the graph goes like this. And 1 to 2, like this. So let's look at, okay, because we need 5, so I'm going to redo it again, guys, so we can see the 5 thing here closely. I'm going to draw it here because my main concern is with the 5. So this is 0, 1, 2, 3, 4, 5, and 6. Okay, that's 1, 2, 3. Okay, great. We are still going to be, hold on, guys. Okay. I'm trying to get a nicer. Okay, I might have to make it here so that I get more space, guys. Okay. 0, 1, 2, 3, 4, 5, and 6. So from 0 to 1, it's like this. This is an open circle. Okay. This is an open circle. Oh, okay. Okay, that's much more better. From 1 to 2, from 2 to 3, from 3 to 4, 4 to 5, and 5 to 6. Okay. Now, what happens at f of 5? Is my function defined at f of 5? Yes. You look at this f of 5. Now remember, f of 5 means, now remember, this is your function f of x. So it means the absolute value of 5 minus 5. And sorry, not the absolute value, the greatest integer. That's the greatest integer function, sorry. So the greatest integer of 5 minus 5. Now the greatest integer for 5 is 5, so 5 minus 5 is a 0. Now remember this graph, guys, this is a graph of f of x. This is the greatest integer function graph. The one which I have drawn is the greatest integer function graph. Now, let's look at limit as x approaches 5 minus of the function f of x. So this is going to be limit x approaches 5 minus. Now, that will be absolute value, not the absolute value, the greatest integer x minus x. Sorry for that little mistake. Okay, so that means the greatest integer of this. Now, this one is simply 5. It's a nice little polynomial. But the greatest integer is all those values which are coming less than 5. That means you're going from 4 to 5. What's the value? It's a 4. So this is 4 minus 5, which is minus 1. Now positive, f positive. So this is f of x, which is basically you're coming from the right-hand side towards 5. So it's absolute, so sorry guys. It's the greatest integer x minus x. Now if you're coming from the right-hand side, that means you're coming from here, the value is 5 for the greatest integer. And this one is simply minus 5, which is 0. Okay. Now remember, this is the greatest integer function. This is the normal polynomial x. Okay. So clearly, we see this one. Is the function continuous? No, the function is not continuous at all integer points. You see that here. So the answer is function is not continuous at, you can see it is. So, sorry, this function is not continuous. That's the only thing we know, because I have not yet drawn the graph of the absolute value of x minus x. But just looking at the left-hand limit, this is, remember, it's the left-hand limit, is not equal to the right-hand limit. Just because the left-hand limit is not equal to the right-hand limit, this function is not continuous at phi. Okay, now let's talk about another function called the absolute value function. Okay, before I do the absolute, the functions here, I'm going to talk about the definition of an absolute value function. Okay, so this is the absolute value. I'm going to start with the simplest definition. The absolute value of x is simply x when x is greater than or equal to 0 and minus of x when x is strictly less than 0. That's the normal definition, and we all know that anything you put inside x, it will give us a positive value. So the graph of this absolute value function is a V shape, if you guys remember. Okay. Okay, now the absolute value which is given to us is an x minus 1. So let's do the math here for that first. So x minus 1 is what? It is x minus 1, that is the whole expression, and x minus 1 is greater than or equal to 0. And it is negative of x minus 1 when x minus 1 is strictly less than 0, which can be done again. So it's x minus 1 when x is strictly greater than or equal to 1, and it is minus of x minus 1. I'm not going to take the negative inside because of a certain reason, and you will see it in a few minutes, when x is strictly less than 1. And the graph of this function is, if you remember from your algebra days, is just a V which has been horizontally moved. Okay. Okay. It's not my day, guys. You can see it. I'm trying to draw it. Okay, fine. Let's just stick it like that. Okay, that's 1. It's basically translating horizontally the graph of original function, which is x, and it is translated to 1 by this little V shape which you see over here. So this is the graph of this function, guys, here. Okay, now let's come back to the problem. The problem says this. It says find the limit of the functions following functions and then find if the function is continuous. Let's start with f of 1. What does f of 1 means? This is my function. Remember, this is the function. It is absolute value of 1 minus 1 over 1 minus 1. It's a 0 by 0, guys. It's undefined. Automatically, we know that. So this is like the, function which is a 0 by 0 form. Okay. If you recall in section 1.3, we talked about indeterminate form. So this is f of 1 is an indeterminate form here. So coming back over here, this once again, this is, I'm going to write, these are all typos, guys, and that's again a typo. Okay, coming back here. So this function limit as x approaches 1 minus of this function f of x. Now here you got to be careful because you're looking at this function f of x. Now this is the absolute value, so that means this is limit as x approaches 1 minus. Now bottom will not be affected, it's x minus 1, but the top you're going to look at the definition of x minus 1. So let's come back over here. So this one, guys, is the definition. So in order to put the numerator, you have to look at values 1 minus. Remember, we're coming from the left-hand side. So 1 minus means we're coming from the left. That means we're looking at this scenario. So the absolute value is now defined as minus of x minus 1. And that was the reason I did not take the negative inside, because I can easily cancel the x minus 1. So what we are is having a limit as x approaches from the left-hand side. It is a minus 1. The final answer is minus 1. Okay, let's go ahead and look at the right-hand limit. The right-hand limit is limit x approaches from the right-hand side. That's 1 positive. This one, the denominator is not going to be affected, but the top is going to be, because you have to go back once again to the definition here. So that definition basically, if you recall, is here. That's the definition. So it's basically x minus 1, which is basically it cancels out. And what are we left with? You're left with limit as x approaches 1 positive, that means from the right-hand side, of 1 is a 1. So clearly, what are we getting? We're getting that the left-hand limit is not equal to the right-hand limit at 1. And hence, this function is not continuous. Okay? Now let's look at another special case. Now here, the question says, find all the values of a such that this given function is everywhere continuous. Now remember, when a function is continuous everywhere, that means it is continuous every point in the domain of the function. Now here, if you look at this one, this function has a problem at 1, but everywhere else on its own, when x are less than strictly greater than 1, it's represented by a line, which is given as 3x plus a. And if it is less than or equal to 1, it is represented by a squaring function. On their own, if it is not at 1, they are basically continuous. But when it is joined together in a piecewise, we have to make sure that it is continuous everywhere. So if you recall back from the previous slide, when we say a function is continuous, what do we mean? We say if a function is continuous, that the left-hand limit should equal the right-hand limit should equal the value at the point we're looking at. So in our problem, guys, notice that this point is represented by 1. So we have to look at what happens at 1, because that's where the change is in this graph. Notice if I just make a graph, just eyeball it, at 1 there is a change. X squared plus 4, I definitely know it's going to be a 13 and it is going to include it. So suppose this is the point 13. Now we do not know 3x plus a. What's happening over here? It's a straight line, but we do not know it's just going to be like this. We know that. The question is, what is this a? Will this a make this whole the same value as 13 or not? Okay. But if the way, according to this, we don't know. But when we read the question again, it says all those values of a which should make it continuous. That means what is this value of a which will get this whole to be a 13? In other words, it's saying that. Okay. Now, so what we know is that if a function is continuous everywhere, what does that mean? That the left-hand limit, which is given by the limit of the function fx, and it's going to be continuous everywhere, but our problem is at 1. So we're just going to focus at 1. It's continuous everywhere. That means the left-hand limit is equal to, okay, let me just make this a little star over here to show you a little, okay, not to confuse you. Okay. Let me just rephrase it, guys, once more. So if I say function is continuous everywhere, That means that the left-hand limit equals the right-hand limit equals the value of the function. Say this is a nice little smiley face. So every smiley face. My smiley face means everywhere. Okay, so everywhere means a smiley face at every point in this domain. Now we'll focus at 1 for that. So in this problem, so in here, we need to focus at x equals 1 because that's a point where there's going to be a change. Okay, so that means the limit of the function fx as x approaches 1 minus, remember that's the left-hand limit, equals the limit of the function fx as x approaches 1 positive, that means the right-hand limit, equals the value of the function 1. Okay, that's what we basically have to do. The left-hand limit equals the right-hand limit equals the value of the function. Okay, so that means we look at left-hand limit. What's the left-hand limit? It's the limit as x approaches 1 minus of the function fx, which is limit x approaches 1 minus, that means we're looking at x squared plus 4, which is limit x approaches 1 minus, or basically you can substitute the values, you don't have to do math more, because it's a nice little polynomial. So it's 1 plus 4, which is a 5. 1 squared plus 4 parts. Remember, you're not looking at the minuses, it is a number. The 1 minus basically means we are coming from the left-hand side. Okay, what's the right-hand limit? The right-hand limit means the limit of the function fx as x approaches 1 positive, which is limit as x approaches from the right-hand side. The function is on the top, 3x plus a, and you substitute 1 here. What do you get? 3 times 1 plus a, which is 3 plus a. Now, what is f of 1? Remember, that's what we're basically looking at. This is what you're saying. Left-hand limit equals the right-hand limit equals f of 1. So basically, I'm writing down the values here. So what is f of 1? F of 1 means look at which the sign has an equal to sign. That's x squared plus 4. So it's 1 squared plus 4, which is a 5. So when you plug in the formula, what are we looking at? We're looking at the left-hand limit equals the right-hand limit equals f of 1, which is basically 5 equals 3 plus a equals 5. So clearly, what number of this a will make it a 5? So a is a 2. Okay, that's the answer, because that is the value 2 which will make the function continuous everywhere. Now one more example, because this a was lying in the function values. Now suppose this a lies on some other place. So we're looking at all values of a such that the given function is continuous, but now my a is the point where there's a distinction for how the graph looks. Now this function, if it is greater than a, all the x values are greater than a, that is a straight line, and if which is given by 3x plus 9. And if you're looking at values less than a, again it is a straight line, but it is given by the function 2x minus 4. So if I want to find where is the function continuous everywhere, so if my function is given to be continuous, that's it, it's everywhere continuous. So function is continuous everywhere, that is function is continuous at x equals a, because that's the point we have to figure out, x equals a. Now from the previous slide, it's the left-hand limit equals the right-hand limit equals f of a. That means the limit of the function fx as x approaches a minus equals the limit fx as x approaches a positive equals f of a. Okay, let's look at this one, a minus. Okay, this one is limit as x approaches a minus so all the values of the function which are less than a, what is the function given by this? It's 2x minus 4. You replace this fx by 2x minus 4. Just to be consistent with using the blues for the right hand and the greens for the left hand. I'm just being consistent with my pen colors. X approaches a positive. This right hand limit is given by 3x plus 9. Now f of a, doesn't matter, let's use the black pen. It's where is the equal to sign lying in the piecewise function. It is for 2x minus 4. So this is 2a minus 4. Now plug in the values, what do we get? We get 2a minus 4 equals 3a plus 9 equals 2a minus 4. So in order to solve for a, we can just pick up, say, these two. 2a minus 4 equals 3a plus 9. I can get the 2a here and all these. So this minus 4 minus 9 equals 3a minus 2a, or minus 13 equals a. And that's our answer. So we have done a lot of problems with special continuous functions. And now, guys, it's time for you to practice. So here are the questions for you to practice. There are three questions, and one of them with 2 parts. So guys, go ahead and practice these questions, very similar to what I have done earlier. Thank you.